We're now going to apply Hessian free optimization to the task of modelling character strings from Wikipedia. So the idea is you read a lot of Wikipedia and then try to predict the next character. Before we get to see what the model learns, I want to describe why we need multiplicative connections and how we can implement those multiplicative connections efficiently in a recurrent neural network. I need to start by explaining why we chose to model character strings rather than strings of words, which is what you normally do when you're trying to model language. The web is composed of character strings. Any learning method that's powerful enough to understand what's going on in the world by reading the web ought to find it trivial to learn which strings make words. As we'll see, this turns out to be true. So we're going to be very ambitious here. We want something that will read Wikipedia and understand the world. If we have to pre-process the text in Wikipedia into words, it's going to be a big hassle. There's all sorts of problems. The first problem is morphemes. The smallest units of meaning, according to linguists, are morphemes. So we're going to have to break up a word into these morphemes if we want to deal with it sensibly. The problem is it's not quite clear what morphemes are. There's things that are a bit like morphemes, but that a linguist wouldn't call a morpheme. So in English, if you take any word that starts with the letters SN, it has a very high chance of meaning something to do with the lips or nose, particularly the upper lip or nose. So words like snarl and sneeze and snot and snog and snort, there's too many of these words for it just to be coincidence. Many people say, yes, but what about snow? That's got nothing to do with the upper lips or nose. But ask yourself, why is snow such a good word for cocaine? Then there's words that come in several pieces. So normally we'd want to treat New York as one lexical item. But if we're talking about the New York Minster roof, then we might want to treat New and York as two separate lexical items. And then there's languages like Finnish. Finnish is an agglutinative language, so it puts together lots of morphemes to make great big words. So here's an example of a word in Finnish that takes about 5 words in English to say the same thing. I have no idea what this word means, but despite my lack of understanding, it makes the point. So here's an obvious kind of recurrent net we might use to try and model character strings. It has a hidden state, and in this case we're going to use 1500 hidden units, and the hidden state dynamics is that the hidden state at time t provides inputs to determine the hidden state at time t plus 1, and the character also provides some inputs. So we add together the effect of the current character with the previous hidden state to get the new hidden state. And then when we arrive at a new hidden state, we try and predict the next character. So we have a single softmax over the 86 characters, and we get the hidden state to try and assign high probability to the correct next character and low probability to the others. And we train the whole system by back-propagating from that softmax the log probability of getting the correct character. We back-propagate that through the hidden to output connections, back through the hidden to character connections, and then back through the hidden to hidden connections, and so on all the way back till the beginning of the string. It's a lot easier to predict 86 characters than 100,000 words, so it's easy to use a softmax at the output. We don't have the problem of a great big softmax. Now I want to explain why we didn't use that kind of recurrent net, but instead used a different kind of net that worked quite a lot better. You could arrange all possible character strings into a tree with a branching ratio of 86 in our case, and what I'm showing here is a tiny little subtree of that great big tree. In fact, this little subtree will occur many times but with different things that are represented by that ... before the fix. So this represents that we had a whole bunch of characters, then we had F, and then I, and then X. And now if we get an I, we're going to go to the left. If we get an E, we're going to go to the right, and so on. So each time we get a character, we move one step down in this tree to a new node. There's exponentially many nodes in the tree of all character strings of length n. So this is going to be a very big tree. We couldn't possibly store it all. If we could store it all, what we'd like to do is put a probability on each of those arrows. And that will be the probability of producing that letter given the context of the node. In an RNN, we try and deal with the fact that the full tree is enormous by using a hidden state vector to represent each of these nodes. So now what the next character has to do is take the hidden state vector that's representing a whole string of characters followed by fix and operate on that hidden state vector to produce the appropriate new hidden state vector if the next character was an I. So when you see an I, you want to turn the hidden state vector into a new hidden state vector. A nice thing about implementing these nodes in this character tree by using the hidden state of a recurrent neural network is that we can share a lot of structure. For example, by the time we arrive at that node that says fix, we may have decided it's probably a verb. And if it's a verb, then I is quite likely because of the ending ing, and that knowledge that I is quite likely with a verb can be shared with lots of other nodes that don't have fix in. So we can get I to operate on the part of the state that represents that it's a verb, and that can be shared between all the verbs. Notice that it's really the conjunction of the current state we're at and the character that determines where we want to go. We don't want I to give us a state that's expecting to get an n next if it wasn't a verb. So we don't want to say that I tends to make you expect an n next. We really want to say, if you already think it's a verb, then when you see an I, you should expect an n next. It's the conjunction of the fact that we think it's a verb and that we saw an I that gets us into this state labelled fixi that's expecting to see an n. So we're going to try and capture that by using multiplicative connections. Instead of using the character inputs to the recurrent net to give extra additive input to the hidden units, we're going to use those characters to swap in a whole hidden-to-hidden weight matrix. The character is going to determine the transition matrix. Now if we did that in the naive way, we'd have each of the 86 characters define a 1500 by 1500 matrix, and that would be a lot of parameters. If we have that many parameters, the net's likely to overfit unless we run it on a huge amount of text for which we might not have time. So the question is, can we achieve this kind of multiplicative interaction where the character determines the hidden-to-hidden weight matrix using many fewer parameters by making use of the fact that characters have things in common? For example, all of the digits are all quite similar to each other in the way in which they make the hidden state evolve. So we want to have a different transition matrix for each of those 86 characters, but we want those 86 character-specific weight matrices to share parameters. And that's a reasonable thing to do because we know that characters 8 and 9 should have very similar transition matrices. So here's how we're going to do it. We're going to have things called factors, and they're going to be denoted by this little triangle with an F above it. What that factor means is that Group A and Group B interact multiplicatively to provide input to Group C. So what each factor does is it first computes a weighted sum for each of its two input groups. So we take the vector state of Group A, which I'll just call A, and we multiply that by the weights on the connections coming into the factor. In other words, we take the scalar product of the vector A and the weight vector u, and that gives us a number at the left-hand vertex of that triangle. Similarly, we take the vector state of group B and we multiply it by the weight vector w, and we get another number at the bottom vertex of the triangle. We now multiply those two numbers together, and that gives us a number, a scalar, and we use that scalar to scale the outgoing weights v in order to provide input for group C. So the input to group C is just the product of the two numbers that come into the two vertices of the triangle times the outgoing weight vector v. We can write that as an equation. The input that factor f provides to group C, so its vector input to group C, is a scalar input to f from group B that's got by multiplying the state of group B by the weights w, f, times a scalar input to f from group A that's got by multiplying the state of group A by the weights u. We then take the product of those two scalars and multiply the weight vector vf by that, and that's the input that the factor gives to group C. Then, of course, we're going to have a whole bunch of those factors. There's another way we can think about these factors that gives more insight into what's going on. Each of the factors actually defines a very simple kind of transition matrix. It's a transition matrix that has rank 1. So the equation we had on the previous slide treats a factor as computing two scalar products, multiplying them together, and then using that as a weight on the outgoing vector v. We can rearrange that equation so that we get one scalar product, and then we've rearranged the last bit so that now we take the outer product of the weight vector u and the weight vector v, and that gives us a matrix, and the scalar product that we computed by multiplying b by w is just a coefficient on that matrix. So we get a scalar coefficient, we multiply a rank 1 matrix by that scalar coefficient to give us a scaled matrix, and then we multiply the current hidden state A by this matrix to determine the input that factor f gives to the next hidden state. If we sum that up over all the factors, the total input to group C is just a sum over all factors of a scalar times a rank 1 matrix, and that sum is a great big matrix. That's the transition matrix, and it gets multiplied by the current hidden state to produce the new hidden state. So we can see that we've synthesized a transition matrix out of these rank 1 matrices provided by each factor, and what the current character in group B has done is it's determined the weight on each of these rank 1 matrices. So B times W determines a scalar weight, a scalar coefficient, to put on each of the matrices out of which we're going to compose this great big character-specific weight matrix. So here's a picture of the whole system. We have a number of factors. In fact, we'll have about 1,500 factors. And the character input is different in that only one of those is active. So there'll only be one relevant weight at a time. And that weight from the current character k, which is called WKF, is the gain that's used on the rank 1 matrix got by taking the outer product of u and v. So the character determines a gain, WKF. You multiply the rank 1 matrix uv by that gain. You add together those scaled matrices for all the different factors, and that's your transition matrix.